So this is kind of longer talk where I want to show you how you can format ISO 8601 dates and times. Kind of, we want to format them fast. So let's take a look. Wait a second. Okay. Yeah. So what is ISO 8601? We format the date like 4-digit year, 2-digit month, and 2-digit day with the leading 0. And we format time as kind of the same way with all 2 digits and with the leading zeros. And date time is formatted like you see below with the delimiter T, which I guess signifies time. And for UTC time zone, you also append Z. So overall, it looks like this, and we will concentrate on formatting this kind of dates and times in 0 time zone. So let's get started. My benchmarks look like this, and this is the variant with the kind of obvious way using streams, and it runs let's say 1x. This will be our base case. So please help me, everyone on the panel, and suggest how fast can we become. What could be the speed improvements? It's more than 40 times.
That was going to be my guess.
Anyone? Okay, that was unhelpful. But anyway, so we just use the stream, set the field character, introduce the set width manipulator for our convenience, and output year, output month, day, with the width of 2 characters, output T separator, and the same way we output hours, minutes, and seconds. And in the end, we restore the field character to its original state. And the next one is actually format leap. And we, instead of using stream, we provide the formatting string to the print call, where we specify that everything except the year should be widened to 2 characters and with leading zeros, and also provides year, month, date, and so on. And this works around 4 times faster. So these times are kind of rough estimations. I got it on my machine. On your machine, they may be a bit different. And so can we get fast? Of course we can. We can ditch the stream and just use format to buffer to measure kind of true speed of format library. And otherwise, everything is the same. And we get around 5.5 times faster than the stream. So can we get faster? Audience? Phil, help me out.
Yes.
What do you think we should use?
Just writing straight into the buffer.
No, what facility to format numbers?
When I did this, I rolled my own, so I may not be.
Okay, we'll get there. This was kind of unhelpful. So let's try the C function strift time. Here we use an object of type TM, which contains all the years and month and so on values. And we supply it like this with a format string that says that we need to format dates with the T separator and time, and then append Z to get our desired format. And it runs around 6 times faster than the string version. Can we get faster? Of course we can. So what if we try to use a compile time format string with format library without changing much else, and we get around 9 times faster than the string version. So can we get faster? Of course we can. We can do it manually. And here you can see that we get in this function all the values like year, month, and so on. We calculate the length that would occupy, that the year value would occupy, and fill the rest with the zeros. So we have leading zeros for years that are less than 1,000, I guess. And the rest is just printing separators and other values with the help of this function that consists of just basically a lookup table where we get the needed sequence of characters using the offset. So here, probably this is an error. It should be n times 2, but it kind of doesn't matter for speed measurement. So we can write this code, and using our manual formatting facility, we can get 100 times faster than the string version. Can we go faster? What do you think, Phil?
You wouldn't be asking the question if
I can't give it away. Yeah.
Didn't FMT?
Yes.
Okay, sorry.
We can get, yes, please.
Didn't FMT have formatting where you can send in the TM?
Right. It used internally. So the released version used internally strf time, and currently they try to optimize to speed up the implementation and ditch the strf time. So now it kind of maybe 40 times faster. I don't know. I didn't measure it. So it's not yet released. So let's get back to our meta. And this version in the previous version, we assumed that the year value can be anything. So if it is like 42, we will have to output 2 zeros and characters 0.2, and it models like general purpose solution. And this version, we assume that the value of the year is less than or equal than 9,999. So it's always no more than 4 characters. So here we just get the centuries by dividing the year by 100 and output 2 characters, 2 decimals, decimal characters. Then we write 2 decimal characters for years, for decades, and for decades, basically, yes. And so on for each value. And also we output separators between the values. And so this version is 330 times, around 330 times faster than the string version. This version is faster than our previous manual version because we don't use two chars from the standard library, and we don't have to assume that the value is random. So we can just use kind of fast path, and only assuming that we have value that will format to no more than 4 characters, we just don't do extra work. And so, can we go faster? I kind of give it away again, and yes, we can go a little bit faster. Though not as much. And here's the full implementation, and let's go through it step by step. This is the kind of core implementation function. It looks like gibberish, so let me explain what happens. We have, you see my cursor. So we have a decimal number that can be presented as A times 10 plus B, where A and B are like single decimal digit numbers. We want to use clever bit twiddling tricks to format 3 values at a time. For this, we need to convert our values to so-called binary coded decimals. For this to do, so each nibble will contain separate decimal digits. For this to do, we have to convert our decimal number, that is x, to our hexadecimal number, that can be represented as A times 16, the same A as in decimal representation, plus B. So we need to find A and B, and actually we need to find Y. So to find A from this system, we can subtract one from another, and we find that A is the difference is A times 6, and here you see the times 6 part. And we can find A just by dividing the x by 10 and taking a floor of that value. So basically integer dividing by 10. And from these two equations, we can find y, which is our decimal number that is converted to binary coded decimal, that will be converted to binary coded decimal. And what we want to do is just take this equation, take x to the other side of the equal sign, and substitute for a. And we get this formula. And this is exactly what happens here with some additional tweaks, let's say. So the first thing that we do, we put the values that we received into spots that are convenient for us. So this is kind of the final destination that the values will eventually get to. And the next step is basically dividing by 10. So here you have, here you can see that by multiplying by 205 and shifting, we basically divide by 10. And for value 2, we get in the interesting byte 0, because 2 divided by 0 is 0. For 12, which is represented by OC here, we get 1 when we divide by 0, and 1 ends up in this byte, in this interesting for us byte. And 21 represented by 1/5 hexadecimal divided by 10 is 2, which you can see appears here. So next we want to mask it off because we want to get only interesting bytes, and we don't want to get the garbage that ended up in other bytes, and we mask it off with this mask. So here we have this masked value with all the tens, and what we are left to do is to multiply it by 6 and add to the initial value. So here you have the result of this operation. And you can see that 21 ends up in the least significant byte, 12, or rather 21 ends up as 2/1 in hexadecimal in the least significant byte, 12 ends up as 1/2 in the byte that will become the minutes or month value, and 2 ends up in the closer to the most significant byte, where it will end up as days or seconds. And so the last operation is swapping so-called low nibble and high nibble of the interesting bytes. And so the low nibble ends up in the high byte, and high nibble ends up in the low byte. And now you have, instead of 21 values 2 and 1, instead of 12 you have 1 and 2, and for 2 you have 0 and 2. Makes sense? Okay, let's continue. We want to format that way both date and time because they have kind of similar format. So we get the kind of formatted value from our implementation, supplying all the values needed. And next thing we need to do is to shift those values into character range. So for value 0, you get character 0. For value 1, you get character 1, and so on. So we are doing this by ORing with this pattern, which is basically adding 3 0 value to each byte, to each interesting byte. And we can supply the separator character and adjust its position with the shifts. So in the end, we have this value, 32 for character 2, 31 for character 1, 2D for character dash, and so on. And so this way we achieve kind of parallel formatting for 3 values at a time. And what we are left to do is to format the centuries, because we can't format 4 values in parallel at a time. And the rest is just tens, decades, and months and days, and hours and minutes and seconds. And we also write the separators. And this is 400 times faster than the stream version. And this is very, very fast and insanely fast. And I don't know any method or idea that can allow to format it faster. So I tried to use SIMD to parallelize even those two operations. They are independent and they, in theory, can be done in parallel. But I have no hardware that is capable to utilize AVX 512 that allows to do two 64-bit integer multiplication in parallel. So I asked Victor to test it, and he wrote that my implementation of SIMD of this algorithm is actually slower than the fast implementation. But I had no chance to tinker with it because I have no capable hardware, so I couldn't optimize it possibly. So is SIMD implementation faster? Is an open question, and that's the end of my talk. Thank you.